Okay. Good morning, everyone. My name is Xuzhe Chen, a postgraduate from Xiamen University. I'm pleased to be here to show our work. The paper I will be presenting today is titled Self-supervised graph representation learning for black market account detection. Okay, let's get started. A multi-purpose messaging mobile app combines several functionalities into a single app to provide integrated service that brings convenience to users. That has become indispensable to mobile users. WeChat, developed by Tencent, is such a representative app with billions of active users. And attracted by the massive number of users, cybercriminals perpetrate frauds in WeChat for illegal profits, causing financial loss to normal users and affecting user experience. And among them, black market accounts, short for BMAS, requires special attention as it causes substantial money losses and is challenging to detect. It refers to such WeChat accounts that are not directly involved in frauds, but provide support service for frauds. And certain cybercriminals create WeChat accounts to sell bulk quantities of WeChat accounts, phone numbers, or IP process that can be used to perpetrate frauds. And typically, the social nature of WeChat makes it a natural choice to model user relationship as a user-user interaction graph. In this way, the BMA detection problem is closely related to the graph-based anomaly detection. It aims to identify the abnormal patterns that deviate from the majorities in the graph domain. So in our task, it is the node classification problem. And however, this task in WeChat has its unique properties and it is more challenging. Firstly, huge and diverse data. Massive users with diverse behaviors are using WeChat. It is a time-consuming and human-intensive process to manually identify BMA patterns. And secondly, demand for generalization. New users join WeChat every day, hence the detection system should adapt properly to unseen accounts. And lastly, lack of labels and great difficulty of manual labeling due to users' privacy. So to solve the challenges mentioned above, we developed a self-supervised graph representation learning-based BMA detection system called SGRL. It mainly consists of an inductive graph neural network encoder and novel structure and attribute encoders based on self-supervised learning. We divide our framework into two phases, pre-training and detection. And we first construct a homogeneous graph where each node represents a WeChat account and each edge indicates user interactions. And node attributes are designed by human experts and form a 7-dimensional binary vector as initial node feature. Given the user graph as input, we first propose and adopt an inductive graph neural network encoder, short for IG encoder here, to learn user representation. Representations of neighboring nodes connected to a user are aggregated by 3 different pooling methods. The results are then concatenated and passed to a single-layer fewer neural network. Specifically, IG encoder adds a self-connection to each node so that the original node attributes extracted based on human knowledge can be retained in the message passing step. And we remove the test nodes in the training graph so the IG encoder does not maintain node embeddings and can be used to produce representations for new and unseen nodes based on their structural and role attribute information. Thus, the IG encoder is inductive. And moreover, to avoid being easily detected, the black market sellers may manipulate several accounts for different purposes like camouflage. However, based on our observation, the same people or the same gang often display similar characteristics. For example, in the figure shown below, the blue nodes appear in the surrounding structure of various clusters. And therefore, we believe it is beneficial to maximize the correlation between a node and its subgraph and encode the subgraph as a context into node representation. And along this direction, we design constructive structure encoders to maximize the local mutual information between the subgraph level summary and the node level representation with graph constructive learning. Specifically, depending on how positive and negative node subgraph pairs are generated, two constructive structural encoders are used in our method. The two encoders share the same encoding module. We use the IG encoder introduced above to generate node-level representation for each node. Then, we choose a simple yet effective design to use the complete k-hop neighbors of the center node as its subgraph. Then with a readout function to summarize these neighboring nodes embeddings into subgraph level representations. A self-supervised objective will be adopted to maximize the mutual information between the center node and its subgraph representations. And the key step in the constructive structure encoder will be the selection of positive and negative pairs. So based on the involvement of the label nodes or not, the strategy differs and forms the two encoder here. The first SSS encoder is designed for the complete self-supervised setting without any labels. Thus, it treats each node and its subgraph as a positive pair and randomly selects another node to generate the negative pair. And the second SS encoder is designed under the supervised setting to utilize the label information. And for each node subgraph pair, it randomly selects another node with opposite label as the negative pair. And besides, the label sparsity is a common challenge in anomaly detection tasks since human labeling is time-consuming and difficult. And therefore, we further design a self-supervised node attribute encoder to alleviate this challenge. The intuition is to use node attributes as the attribute level supervision to alleviate the reliance on the label level supervision. Specifically, we first adopt the well-known gradient boosting algorithm XGBoost to estimate the importance of each attribute to label prediction. Then we pick two most crucial attributes as such pseudo-labels for each node. We then formulate a new graph-based multi-label prediction task with missing label as a self-supervised learning task. Its main idea is to use the attribute and the structural information of the neighboring nodes to predict the pseudo-labels of the center node. Similarly, we use IG encoder for node encoding and utilize a multi-label prediction loss for optimization. And that's the end of the pre-training phase. Putting all together in the detection phase, we concat the representations generated by the constructive structure encoders as additional node features and replace the two attributes marked as pseudo-labels with the predictions of the self-supervised node attribute encoder. And in this section, we gave a demonstration of the experiment setting and results. And we extract data from WeChat and construct a user iteration graph. The graph contains nearly 4 million user nodes and 13.4 million edges. And among them, about 100,000 user nodes are labeled, and half of them are labeled frosters. We compare our proposed method with various baselines and use several matrices to fully evaluate the performance of each method. And the experiment results are listed below. We can see that GN methods generally outperform non-GN methods, indicating the benefit of introducing structural information. And besides, introduced self-supervised learning can further improve performance. And our proposed method achieves the best performance, which is in line with our analysis above. And moreover, we conduct evaluation study to verify the contribution of each component in SGRL and explore different settings of self-supervised and subgraph selection as well. And here, the definition of each subscript can be referred in the original paper. And from the results, we can see that one-hop neighborhood performs better than two-hop. As larger subgraph may introduce noise and first-order neighbors are more important. And among different constructive settings, no subgraph level reaches the best performance, which is in line with our observation of the black market accounts behavior. And we also explore the impact of fewer labels. And the figure indicates that with limited labels, SGRL can still consistently provide accurate predictions. And the data visualization shows a clear distinction. And we conduct an online test to detect BNAS over the WeChat graph once every day within a month. The result reveals that it gains 7.27% improvement in the matrix detection success rate compared to the before mere IG encoder. And in conclusion, we analyzed the scenario of black market account detection task and applied graph-based method for solution. And we proposed novel structural and attribute encoders based on graph self-supervised learning to fully model the user behavioral pattern. And experiments on data set extracted from WeChat demonstrate that HRL clearly outperforms the state-of-the-art baselines. And that's the presentation of our paper. Thanks for listening.